All right. So we finally get to drug analysis, right? We've been waiting. We've done quality and all this stuff. We've looked at instruments and so on. And then what do we do first? We don't even use the instruments. So we talked about all those instruments, but we're going to talk today about presumptive tests. So when you take this test, you get a color change or something like that, and you presume the presence of a drug based on the test. It's not a confirmatory. So those are the two words there. It's presumed to be a controlled substance if you get a color change using these colorimetric tests, but you have to confirm that presumption. So this isn't enough to, be definitive. You have to have at least, two of these plus one confirmatory test, or one of these plus two confirmatory tests, or you could just go straight to the confirmatory test. But a lot of times these presumptive tests are used to screen things. Got a white powder on the floor at HEB, run it through a few of these tests, no color change. It's probably flour, probably sugar. Yeah, something not a controlled substance. Okay. Now, that being said, you always take into account what they call the totality of circumstances. So a white powder on the floor, not necessarily suspicious. It's what are the circumstances around that? If you just opened your mail and you look down, you're like, wait a second, what's in my mail? And so right after 9/11, there was a big rash of anthrax attacks. Somebody was sending letters with anthrax in them. And so then we had all this thing. How do we scan mail for anthrax? How do we sterilize the mail? So anything biological inside the mail would be killed before the person opens it. So it was a really big disruption. And that was sort of overshadowed by, 9/11 and the other things that were going on at the time. But anyway, so white powder coming out of your envelope, definitely totality of circumstances, that's suspicious. White powder on the baking aisle at HEB, probably not suspicious. Here's another thing that's suspicious. If you're ever at a tank exchange, or if you ever see a propane tank with a blue handle, beware. Okay, this isn't in the book, but it's related to color changes. And when you see blue brass, that's a problem because it's been exposed to ammonia gas. And ammonia gas in a clandestine meth lab, they use ammonia gas to do one of the steps in the synthesis of methamphetamine. And they steal it from agricultural places, like a farmer may, if he's got a large field, buy a large tank of anhydrous ammonia and have it stationed at his field so he can fill up his tractor with the jets that put it into the soil. But you've got this large tanker truck of anhydrous ammonia out in the middle of the country. And so people who want to steal some of that have the piping and everything, they hook up to that truck and they steal some of the ammonia. Well, a lot of times they use propane tanks, and that's inappropriate to use because it has brass valves and ammonia will attack the brass valves. So this is evidence of a clandestine meth lab. When you see brass valves on a propane tank that are turned blue, it's the copper in that brass that's reacting with the ammonia. And so this is the ammonia complex that you're seeing. It's a blue color. So because this is a color change phenomenon, I put it in this set of notes. So it's just personal, because the inside of that brass valve could be completely corroded and it could be paper thin. So even to try to test it, like pop it open, you're taking a huge risk. So just don't even mess with that valve. Call somebody or take it to I don't know where you would take it. That'd be a good question. Call the sheriff and ask, where do you want us to take this? Because I don't want to crack it open, because the whole thing could pop loose and you get a blast of anhydrous ammonia in your face. That will kill you. So you'll cough so hard, and it will turn to base in your lungs, like concentrated anhydrous ammonia. When it gets in the water, will turn into ammonium hydroxide, and that destroys the tissues of your lungs, and that's how you die. It's chemical pneumonia. Not good. Okay. Now, thank you. This is presumptive tests really classify drugs. Like, you might not know which opiate, you'll get a hit for opiates. You might not know which cannabinoid, you'll get a hit for cannabinoids. So this is one way to classify drugs. Colorimetry and precipitation, these are tried and true methods. Okay, getting color changes according to the drugs or the substances, looking at their color directly with reflectance spectroscopy. Functional groups. Now, in organic chemistry, you spent weeks and weeks and weeks learning functional groups. Is it an aldehyde? Is it a ketone? Is it an acid or a base? Um, that's great for classifying organic molecules, but it's too complex for drugs because they have multiple of those. So if you look at it, we'll look at some drug structures, and you'll see that it's not. Just look at the flashcards. It's not going to be a useful thing to say. Um, this drug is an alcohol because so many of them are alcohols. Or this drug has got a fused ring structure. There's so many that have that. Acid base neutral classification is common because of the extraction methods used. So we talked about that. Is this drug a base? Is it an acid? Is it both? So that's pretty helpful. And then there are secondary classifications like the effect of it has. Is it a depressant of your central nervous system? Is it a stimulant? So those are effect classifications. And then schedule, like the federal schedule or maybe state schedules. A schedule in government vocabulary is a table. So whenever you hear a schedule, don't think of like Outlook, what you're doing during the week. It's a table. So like the tax schedule, that's a table of tax rates. And the drug schedule is a table of various classifications of drugs. And so that's another way to classify them. We're going to focus on the chemistry, not the analytical methods, because there's whole volumes and desk references of forensic methods for analysis. And we have some in our library. So if you're ever curious about that, you can go to the orange, let's see, what's it called? It's the catalog searching thing that you have on the Newton Gresham Library and type in forensic analysis methods. Boom, you'll get all of these books, and you can go, just if you're bored, go thumb through them and you can find ways to analyze all these different drugs and other substances. Yeah, orange, engine orange. Yeah, I knew it had orange in the name. So you can type in your forensic analytical techniques, hit search, you get a whole bunch of them. So here's some of the drugs, just to kind of show the point that using functional groups is going to be difficult, right? Because this is one of the metabolites of cocaine. I know that because it has this tropane ring structure here. Okay. Propane. It's also an acid. It's also a base. So you got a substance that's in two categories. So is it an acid? Is it a base? It's amphoteric. It has both. Okay. You have some that are alcohol, some that are acids. You have some that are, what is this fused ring structure? Who knows, right? I mean, how would you name that? I mean, I'm sure there's an IUPAC version of that name, but it would be a nightmare. Okay. Okay. So, but it's because this is an extraction from the cannabis plant. You've got all these different cannabinoids that come from that plant. So this would be classified by its origin. So it's a cannabinoid. Here's morphine, again, from the poppy plant. So this would be an opiate. And then we have the synthetic drugs, which again, they're not classified by origin. We really just have to name them straight out. Now, sometimes they are classified by their effect. Like here's a selective serotonin reuptake inhibitor, SSRI. And so that's the effect that it has. And so you would have a classification of those substances that fit under that grouping, SSRIs. There's a bunch of them. So classification is a pretty tricky business. There's lots of different ways you can classify these substances. What I would like for you to do with the note cards or flashcards that I put up on Blackboard is print those off, cut them up, and look at them. Or, if somebody wants to put them into Quizlet or something like that, then let us know that you could share that group. Or if y'all want to do that as a group, then we'd have a Quizlet one. Have you ever used Quizlet with the flashcards? It's fantastic. And then what I want you to do is to be able to see this kind of molecule. It might have different things here at the bottom, OH or an acetyl group or whatever, and you have heroin and you have codeine and hydrocodone and so on. But those are all opiates. And so I would like for you to see this molecule and think opiate. If I tell you opiate, I'm not going to require you to draw it like from scratch. Okay, but you need to be able to recognize it. So that's the level I think is appropriate for all of these substances. You're coming into this pretty cold, boom, you're going to get all of these molecules. What do you do with them? I want you to recognize the types of molecules. If you see that tropane ring up there, it's cocaine or a metabolite of cocaine. It's something related to cocaine. So that's what you would select if you were asked that and you're given several options. You would say, okay, this is one of the cocaine molecules or metabolites. If you see a molecule like this with this three-ring structure and a tail, then you're talking about a cannabinoid. And so that's the level of familiarity that I would like for you guys with the different drugs, because there's too many to learn like that. We would spend the whole semester just drilling on which kinds. I mean, just the cannabinoids. There's now like 10 or 15 of them where you can go through and have, you know, an acid here or some other kind of ethyl group here or something like that. And then it gets into the delta 6 and the delta 9s and all of these different cannabinoids. And it's, I mean, it's too difficult, I think, to just from cold standstill to learn all of those. And plus, your recognition, I think, is the real thing. If you can recognize those, you walk into a room and you see someone's got one of these molecules on the top, you know they're talking about opiates. Okay. Here's some new ones, fentanyl. And this is a picture of a poster that one of the grad students did using Gaussian to model the spectra of fentanyl. And I wanted to highlight this section down here because this is how she showed the structures of fentanyl, and you'll see this in the papers that deal with a lot of these different molecules. So I wanted to test you guys on this so that you know what's going on in a figure like this, because it's a pretty complicated figure. There are 1, 2, 3, 4, 5, 6, 7, 8 different versions of fentanyl shown on this. They're different analogs, and so they're fentanyl analogs or fentalogs. And this is the way that Madison decided to put this structure in this poster. And she was going along with what's the standard practice in a lot of the literature too. So let's try to build let's build acetyl. Yeah, let's build acetyl fentanyl. Okay, so let's build this green one here. So we start out with the base structure. So this is the base structure. And so we're looking at the green one. So the green one here will have this acetyl group on here for R1. And so for R1, we put this carboxylic acid or carbonyl group with a methyl group on it. Okay, so that's R1. And then R2, since this yellow one only goes with the norfentanyl down here. So that's the only time we use the yellow one. All the others we use this here. So we have this down, over, down, and we've got a phenyl group on it. So do you see how to use the key? You just change the R groups, and now we have an R3. This pink one goes with this cis-3-methylfentanyl, so we put an H there for R3. So we have an H. And so what we've drawn there is acetylfentanyl. Do you see how it works? You just have the 3 R groups, and you look at the key, and the color key tells you which one of those to use. Would I ask you, okay, draw butyrylfentanyl from scratch? No. But if you have the key and I say draw butyrylfentanyl, you should be able to do that. Or if I show a molecule and say, which one of those is this molecule, you should be able to say, okay, what's in R1? R1, okay, I've got that acetyl group here, so that's the green one. And I've still got this for R2, and I've got an H for R3, so definitely that's this green one, it's acetylfentanyl. Okay, homework and a potential test question. So color tests are still used. We use visual examination and photography and microscopy to analyze these substances. These are presumptive tests, also called spot tests or screening tests. And most are colorimetric. and they have these different reagents that we use. Here's 4 reagents. There's many others, but these are four common ones. Excuse me. And so how to pronounce this, I really don't know. It's one of those things that when you have a word that you see, but you've never heard anybody say it. So, yeah, so Ducanol, I don't know. Ducanolvine, I don't know. I'm not a French person, but maybe someone can help me out with it. Cobalt thiocyanate, I've got that one. The marquee reagent for opiates and PDMAB for LSD. So let's look at the reactions of these and what causes the color change. Now, these also must be followed by confirmatory tests. GC, LC, FTIR count as one confirmatory test. So think about that. That's just GC. It doesn't say GCMS, liquid chromatography. It doesn't say LCMS. That just counts as one confirmatory step. So how would that work? Well, we do, let's say with cocaine. We do a cobalt thiocyanate test for cocaine. It hits positive. So we have cocaine and other alkaloids, but the color test, like you look at the specific color and it says cocaine. So we've got a presumption of cocaine. And we dissolve some more of that substance and run it through a GC, and we get a retention time for cocaine. So we have cocaine standards. We see when that retention time would be, and then we get a retention time from our unknown. So that's 2 points that are unrelated. One's the color of the substance when it reacts with this reagent, and the other is the retention time in a GC. And so that's a one confirmatory test. But it could be that something else, because all it's doing is separating it based on its affinity for the mobile phase and the stationary phase. So there's nothing really tying it exactly to the structure of cocaine. It's the rough polarity of cocaine and its boiling point if it's GC, right? So it's best to have 2 confirmatory tests. Now, if you put a mass spec on the end, you have two data points. For GCMS, you have the retention time and you have the fragment pattern. So that counts as 2 tests. So that's why we love GCMS. Yes, it's expensive, but you get 2 tests out of it in one run. You get 2 data points. Did it come out at the right retention time? Check the box. It's cocaine. Did it have the right fragment pattern? No. That's inconclusive. But if it did have the right fragment pattern, then you got 2 confirmatory tests, and then you can say safely that it's cocaine. Okay, the nice thing about spot testings, colorimetric spot testing, is your eye is very sensitive to color changes, especially in the green region. If you were to take spectra of some of our acid-base indicators like bromocresol green, it's yellow. Well, don't get me lying. I think it's yellow in acid and green in base, but it could be reversed. Okay, but anyway, the point is it's yellow and green. And you just change the pH a little bit, dramatic color change. You look at the spectra, there's just a tiny little difference in absorption in the green area. And your eye says, whoa, that's a really different color. So not much change in the molecule and the color spectrum can give us a perceived huge change in the color that we get. So it doesn't take much for us to see dramatic differences at the molecular level if color is involved. This gets us down to 1 to 50 microgram detection limits, and that's good too, because even some of the more deadly analogs of fentanyl, I think carfentanil is one of the most deadly, where your lethal dose absorbed through the skin can be in the milligram ranges. So a milligram can be just a few little specks on the table. You wipe your fingers on the table and then you can't breathe, okay? Because your fentanyl will specifically attack your lungs and your brainstem. It'll stop you from breathing. And so it'd be nice to be able to detect something way below the milligram range, and this can detect into the microgram range. So that's really nice. So that's very good. Of course, this is a downfall for these kinds of tests because experience is needed. Like the first time you do it, you can follow the procedure and you think you're doing it right. The 100th, 1000th time you've done it, you've seen 1,000 of these and you know how long to wait. Sometimes you put the reagent on there and you have to wait 15 seconds or 30 seconds for the color to develop. And then you've got to read it within 1 minute, because then the color fades or changes. So there's a window at which you should read the test. Just like remember the COVID test, you had a certain window to read the color change. It said, wait so and so many seconds, but you can't wait too long, and so on. It's exactly the same thing. Okay, inexperience can lead to inaccurate results, for sure. It can fade over time. And then this can also be easily adapted to TLC as a spot developer. So as we talked about with thin layer chromatography, you get separation in your spots, but a lot of times the organic compounds just look kind of yellowish, right? You've got white light hitting it, but some of the functional groups are absorbing the UV and a little bit of the blue, and that's enough to give it a slightly yellow color. And that's what happens. I don't know if you have any memory of childhood where you've got something in the window and it fades and yellows. What's happening is the UV light is destroying that molecule, oxidizing it, and you're getting carbonyl groups and you're getting aldehyde groups in there, and those absorb a tiny little bit of the blue, a lot of UV and a little bit of the blue. And so then something white exposed to the sun will yellow over time because of the functional groups that are developing from oxidation. This is nice. If we could coat a wipe and wipe the surface and look for a color change, that would be fantastic. We tried to do this in our lab for looking for oxidation sources in people's luggage. Like if we could spray the wipe that they use for wiping down your luggage and testing for explosives, if the wipe had a color change, like let's say you don't have an explosive, but you've got a lot of potassium chlorate, which could create a fire that couldn't be put out on a plane. That would be a problem, okay? And if you're testing for explosives, you're probably not testing for chlorate. You're testing for other explosives. But if the wipe is wiping down someone's luggage and it is a color change, then, hey, we need to look inside this bag. They try to keep the inspection of your luggage going through the airport. This was a few years ago. At that time, it was 6 seconds. So they want 6 seconds to inspect each bag. And so it's got to move pretty quickly. So a lot of bags take 2 seconds so that you can spend 10 seconds on something that looks a little fishy. Well, we had the color change agent. It was we used the iodate system, and it produced iodine and starch. So that's what it was. When it reached when it was oxidized in the presence of an oxidizing agent, it produced free iodine, and then that reacted with starch and gave a black color. So the wipe turned black if you wiped something that was an oxidizer. The downside was it had to be wet, because the molecules have to get close to each other to react. Okay? And solid molecules just sit there, it's kind of like a middle school dance. They're not going anywhere near each other. You got to have something to get the party started. So we needed to spray it with a developer. Well, then now you got a wet wipe, and you're not going to stick that in the IMS. And so they would have to use 2 wipes, 2 wands, and all of that. So we thought this probably isn't going to go anywhere. But we published it. But anyway, wipes would be a great idea, but you're still probably going to need to spray it with something to develop it. So you can wipe the surface and then spray it with a detector and then see if it develops a color. Now, these are some new vocabulary words for you in terms of the appearance of color. So it's related to the peaks that absorb the visible light, and when they shift, they give a bathochromic shift, a hypsochromic shift, a hyperchromic shift, or a hypochromic shift. So chromic is used in all of these, and we're not talking about chromium, we're talking about color. So what do you think hypercolor means? It gets more vivid, stronger colored, and hypo means less colored. And so you'll see this in some of the descriptions. Read before 30 seconds, or read in 30 seconds before a hypochromic shift happens, or whatever, before the color fades. They could just say color fades, but I think they want to sound very technical. Okay. And then bathochromic, and here's wavelength. So this is long wavelength, and this is short wavelength. So bathochromic, so that would be a red shift. And that doesn't necessarily mean it becomes red. It could go from blue to green. Blue to green is a red shift. Green to yellow is a red shift. So it's going towards longer wavelengths. So all of those would be bathochromic shifts. Blue going to a blue-green, to a green, to a yellow. All of those are moving that direction towards longer wavelengths. So those would be bathochromic shifts. And then hypso, I don't really know what hypso is, but I'd say it's short wavelength. It's definitely shorter wavelength. So if it goes from green to blue, that's a blue shift. Okay. And so if it goes from orange to yellow, you really got to know Roy G. Biv, right? So it's orange to yellow or yellow to green. That's a hypsochromic shift. It's going to shorter wavelengths. Okay, and then we have these different names for the colorants that happen. So we have pigments and dyes. So it's really based upon the matrix. So a colorant that's insoluble in the matrix is a pigment. And a lot of those in the past have been inorganic, like clays and stuff. You suspend them in water, spread it, paint it on the substance, the water evaporates and leaves the pigment behind. And a dye is a colorant that's soluble in the matrix. And the interesting thing is it has nothing to do with the molecule itself, it's the matrix that it's in. So a molecule could be a dye in water and a pigment in organic solvents, or vice versa. It could be a dye in organic because it's organic soluble, but if you could get the particles small enough to be suspended in water, it would be a pigment in water. So it's not a property of the colorant substance. It's a property of the matrix it's carried in. So if it's carried in a matrix where it's insoluble, it's a pigment. If it's carried in a matrix that it's soluble in, that's a dye. Okay. And we'll get to that some more in the paints and ink analysis later when we talk about paints and polymers and so on. So this is the meat of today's lecture, is these 4 families of dyes. And then we'll add metal colorants too. But I think this is the main thing we spend our time today on. And that is, you must recognize these. Because this would be not a classification of the drug substance, this is a classification of the colorant or the color phenomenon that you're seeing. So here are the 4 families of dyes. And triaromethine. So we have 3, and it could also be dye. So diaromethynes and triaromethynes. This is aryl, okay? So that's aromatic rings. Right, we see these right here. And then the methine. That's this carbon bonded to 3 things. So you got methane and methine and so on. So this is the carbon. So that 3 aromatic rings connected to a carbon and probably charged. So this charge can hop all over the place using resonance structures, and a lot of times we'll put it right there on that carbon. So the charge will be on there. Okay, so that's the triaromethynes. Sometimes you see diaromethynes. Then we have azo dyes. These are super easy to find because you have this azo group. This one, the way they've drawn this molecule is kind of a problem because you've got so much steric hindrance. Notice organic chemists are so lazy, they drop all the hydrogens off, and these hydrogens would be bumping into each other. So it wants to be planar, but you've got some steric hindrance, so you're going to have to rotate those rings a little bit. This is the cis conformation. The trans conformation is almost always preferred. So you've got the molecule over here. What causes this to be colored is these non-bonded electrons on the azos. And so they will undergo an N to pi star transition. So they'll go from non-bonded to the anti-bonding on that nitrogen double bond. So we've got, instead of a double bond that locks this structure into what it wants to be a planar structure, when we activate that anti-bonding orbital, now that azo group can rotate. And that's actually how the vision works in our eyes. We have azo pigments or dyes, azo molecules in our cones and rods, and light hits them and causes that azo group to be flexible. And so that molecule, when it hits the antibonding orbital, it's absorbed a photon of light, will go to an excited state, and that rotation is enough to kick off a nerve signal. And so we can detect single photons with our rods and cones with these pigments that pop every time a photon comes in, and it causes that N to pi star transition. So that's pretty cool. Then we just have, nitro dyes and things like that. So nitro, and I'll go ahead and say nitroso too. Nitro and nitroso, so an extra SO on the end. So a nitroso group would be this, an N double bonded to the oxygen. That's a nitroso. And those can also be strongly colored. So you're looking for a nitro group, often tied to an aromatic ring, or a nitroso group tied to an aromatic ring. And then this one says carbonyl dyes, but carbonyls by themselves aren't necessarily causing color changes. I mean, think about acetone. It's a clear solvent, so it's not colored. So the presence of a carbonyl doesn't really make it a colored substance, but when you put it in with an extended pi cloud, so you've got this pi cloud here, and you've got a carbonyl attached to it, then you've got this electron transfer, which is a pretty strong absorber. So you've got an N to pi star transition again. So this non-bonded electron gets donated into the pi cloud, and that's typically what's seen for the strong absorbers. And so here we've got another one. We've got these non-bonded electrons. We've got an extended pi cloud, and the N to pi star goes in, and you get an absorption of photons. The reason that these are strongly colored is that the pi cloud, it's kind of like particle in the box thinking from PChem 1. The bigger the box, the closer the energy levels. Okay. A carbonyl N to pi star exists, but it's in the UV. But if it's donating to a bigger box, like an extended pi cloud, those energy levels are closer together. So now this N to pi star transition is in the visible range. And so we see a color change. So light comes in and you see a big, huge absorption peak. N to pi stars are pretty big absorbers. And so you get a really strong color from this molecule. So those are the 4 families of dyes. Before we get into the individual tests, are there any questions about recognizing any of these? Yes? Oh, I thought you raised your hand. Okay. The only one that I think is well, the top 2 are pretty subtle, right? Trying to find that aromethine, the methine part. I mean, you got a bunch of things here, but you may not see up there. You don't see any azos. There's no nitro groups or anything like that. What is it? Well, I don't see a carbonyl either. So by elimination, it's going to be the triaromethine, but that's not very satisfying. You're not. When you're taking the test and you're putting the question mark in the margin because you don't really know if you got that one. Okay, that's doing it by elimination. You're gonna have to put a question mark. But if you find that carbon bonded to 3 aromatic rings, it's a triaromethine. So just look at the molecules and you'll see. Yes. Yeah, and so it would be in both categories, but many times the azo wins out, but yeah, you could say yes, this is also in a nitro category. Yeah. And that's it. I don't see any carbonyls on an extended pi cloud. Now, if it had a carbonyl on it too, let's just make this chlorine and oxygen and put a double bond on there. Forget all the other mayhem that would cause. It's really not much of an extended pi cloud. So I would say that would be the weakest component would be this carbonyl, because it's not donating into a large pi cloud. And so it's probably not going to be in the visible range. It might be close to the blue range, but it's not going to be into the visible range. But the azo dyes and the nitro aromatics, those are going to cause pretty strong colors. So let's look at the reactions. So here's the difference between cold medicine and methamphetamine is not very much. If you look at that, you know, there's just this methyl group here on that nitrogen. Okay, and the Marquis reagent attacks this aromatic carbon that's para to this functional group here. Okay, and what does it do to it? Well, the reaction comes and it makes a dimer. So see, here's a dimer here, and this is a diaryl methine. And the only difference between these two is the presence of a methyl group here and here. But this cold medicine starts out orange-red and turns brown in the color change. You know, as you do this test, if you're trying to test between cold medicine, which you could have in your cabinet or whatever in your backpack, or methamphetamine, you get a different sequence of colors. It starts out orange-red and then turns brown, and then the methamphetamine goes straight to orange, not orange-red. So you can see how experience would be important there. Is it orange-red or is it orange? Am I dealing with a cold medicine or am I dealing with methamphetamine? Okay. But dimerization is what happens a lot of times. And then they'll dimerize even further, maybe make a trimerization. Okay, let's look at the morphine with the Marquis reagent. Now, this one, again, this is a figure from the book, but I tried to help you out by showing where the reaction takes place. So this is morphine up here, and it attacks this double bond right here on this fused ring. Okay, and that's where it dimerizes. So you see now we have two morphine molecules joined right there. Here's one and here's two. Okay, now how would we classify this thing? Well, we've got some carbonyls on here and an extended pi cloud. So this carbonyl is going to donate into this extended pi cloud. And so I think this is going to be a carbonyl type colorant. So you react it with formaldehyde and this Marquis reagent, and then you add sulfuric acid and you get a violet color. Okay. Let's look at Ehrlich's test. This is testing LSD. So this is LSD. And again, I'm not going through all of these reactions so that you could like rattle them off. They're pretty complex. But I want to show you, like in this one in particular, how scientists try to simplify things. So look what they've done here. They've put this wavy line right here to show that this part of the molecule is not important. Okay, so this PDMAB comes in and reacts with this carbon here. And so now that this molecule, I'll call that, well, I don't know, it's this piece right here. And this is the LSD, and right here, LSD. And so that wavy line just saves them the time of putting all of that stuff on there. They're just showing you what it reacted with. Okay. And so then we add some acid, we lose a water, and then we formed this diaryl methine. we can react it again and put another LSD molecule on there, and then pull out hydrogen upon adding acid. And so then we end up with this triaromethine. You can see the methine part is right here, and then the three aromatic systems surround it. Okay. At this point here, we probably get a color change too, because this is a diarrow. And so this is how PEDMAB detects LSD. Okay. Okay, here's phenols and amines using the Lieberman test. And so once again, I've highlighted here's a phenol here, right here. So this is phenol. And then this is the reagent. So the reagent attacks here and forms this extended pi cloud that extends the box for those electrons. Their energy levels get closer together. And remember, most of these molecules absorb into UV. So when we extend the box, now those absorptions move into the visible range, and we have a colored substance. So you get absorption peaks in the visible range, and then you see a color. Okay. So this one is acid base. This basically makes an acid base indicator. It's red in acid and blue in base. Okay. And this would be a carbonyl dye because you've got the N to pi star transition. Here's the Simon test. So this is methamphetamine. Again, it's been reduced to just R. Okay. So this part is R prime. This is the methyl group or hydrogen if it's just amphetamine, and it's reacted with this nitrogen group. So this is the first reaction, and we create this active carbon, which then reacts with this ferrocyanide group. And so we have, this is the drug molecule right here. And then this iron is our metal coordination complex. And so that's the d electrons in the iron that are given the color. So this one isn't our four grouping of organic dyes or colorants. This one has an iron complex that's put on it, and it gives you a blue result. And then lastly, the marijuana with the Ducanal reagent. Here it's showing the active or the target atom in this particular, in THC. So it's going to hit right here and put, again, more pi cloud on there. So we have this extended pi cloud. And so then we've got non-bonded electrons here on this oxygen, this ether. We've got non-bonded electrons there. And so we get the N to pi star strongly colored transition. Notice in the THC and all the other cannabinoids, we've got some non-bonded electrons here, and we've got some here, but the pi cloud is not very extended. So those energy levels are in the UV. But if we could extend that pi cloud, then all of a sudden the energy levels drop into the visible range and we get a color change. We go from a colorless substance or a white substance or maybe off-white, a little yellow, to a strongly colored substance. And then it's very sensitive too. So this is THC. If it was THCA, in other words, the acid, then this piece right here has been turned into an acid group. And again, it's going to be a very different color because you've got a different pi cloud and different energy levels, and it doesn't take much to shift those peaks in the visible range. What is that? You'll need to tell me when that stuff pops up. How long has that been there? Okay. Yeah, I figured. I don't know what I hit, but I saw it behind me on the little camera here. But, oh, what's this? Yeah. Okay. And now, as far as a This is a lazy way to do it too. So you could also react it with fast blue reagent, and fast blue comes with its own azo. Okay, so here it is. It's an azide, and then it reacts to form an azo. And it's not very selective, so it's going to hit that aromatic ring on THC, and so it's going to hit this carbon here or that carbon there. And so look how lazy they are. They don't put it to either one of those carbons, they put it to the center of the ring. And I show you this one specifically because that's sort of saying it could form either one of those. We don't need to draw both. We'll just say it hits that ring. So that's the ring it hits. But don't you think that that is going to be like bonded to space in between the ring? Okay, that's not what they're drawing here. It's a lazy way to draw the molecules. So that's really the main point today, was to learn the 4 classifications of the different colorants, to add in a couple of inorganic ones, like the copper ammonia one for the propane tank and brass valve, and also the Simon-Aw complex that has the iron in it. And then to show you some of the ways that we draw these really complex reactions, like the wavy line in LSD, to sort of just eliminate half of the molecule, or this one, where they show a moiety, a chemical piece that's bonded somewhere on an aromatic ring. They'll just point to the ring. I mean, they didn't point here, they didn't point here. So we know it's bonded to that aromatic ring, and it's probably not displacing these 2 items. So it's going to be on that carbon or that carbon. These other items, that's the little wiggly tail on the cannabinoid, okay? But this guy right here changes quite a bit depending upon the different cannabinoids. And so that's what gives us, and also this ring here can open up or close, whether it's CBD or THC or those kinds of things. So this ring can be different. And those are the things that create the different colors. So we could extract the green plant-like material. That's what GPLM is, green plant-like material. Okay, with ether, spot a TLC plate and elute, and then you can spray those spots with fast blue, and you'll get THC and all the other components. Maybe you get the 3 main components or a bunch of others. Now, let's talk about colorimetry. We did the color lab, the RGB color lab, so let's review a little bit of that. This is the freshman level colorimetry, where if you have a big absorption peak in the yellow part of the spectrum, you're going to get blue light and red light through that substance. So if it absorbs the yellow, it's going to look purple. And so that's what we have with the color wheel. If it absorbs the yellow in the 570 range, then you're going to get light that you might interpret as a wavelength of 420, but it's not necessarily the light only at 420. You're getting a little bit of red in there too if it absorbs in the yellow. Okay? If it absorbs in the green, you go straight across, it's probably a red substance. If it absorbs in the blue, it's a red or orange substance. And so you just go across the color wheel. But this doesn't tell you what you get when you have multiple peaks or asymmetric peaks, or strongly colored substances can saturate the spectrum, and then their color starts to change when they see what's a good example of that. Or even rough substances like powdered substances. So potassium permanganate, you know potassium permanganate. It's one of the darkest purple substances you can have. If you have potassium permanganate crystals, they look black because they're absorbing so much light. Spread them out on a white piece of paper, then you can see that they're beautiful purple crystals. Okay. What if you rough them up? Like if you have them in as small crystals in a jug, and you're breaking up the surfaces of those crystals and making them rough, they will start to look pink. If you rough them up really well, they might even get all the way to white. Even though the substance in itself is purple, when you powder it, you don't get very good absorption. You get more scattering. And so you're not getting the color, you're getting the surface roughness. Okay. Peak shape can make a huge difference. And this was such a big deal that we wrote a paper on it. So the Beyond Lambda Max Part 2, Predicting Molecular Color. So you have the RGB lab, and this is the second half of that. So if we simulate a spectrum of a molecule, we might get a lambda of the absorption, a wavelength of absorption, and to say that it absorbs at 500 is going to give you a certain color can be misleading if your peaks are asymmetric. So this peak here is at 550 nanometers, okay? But if it tails to the long wavelength, if it's skewed, you see the dotted line, if it scales to the red, we get a lot of blue light through and we absorb a lot of the red. Even though the peak maximum is at 550, this dashed line would give a blue substance because it's tailing to the red and it's absorbing red as well. If it tails to the blue, we get just the opposite. So the peak maximum is still 550, but because the peak is asymmetric, this substance would appear red. So isn't that weird? You get the same peak maximum, 550. And depending upon the asymmetric shape of the peak, it could be red, it could be blue. So lambda max isn't enough. You need to know the shape of the peak to predict the color of the substance. And so that's why we want to take spectra. So this is the sort of the instrumental side, bringing that back in. And in that RGB lab, you know, what I was going for was the numerical color, okay? And so these are the RGB values, red, green, blue values. And you see it starts out pretty like with one molecule, but if you concentrate it, then it saturates and becomes a blue substance. Here, it starts out with a very light white color, but if you saturate it, it goes through pink and becomes red. But you see, these are numerical values for red, green, and blue. So I know those pixel values, and I can type that into my computer, and that's a superior way, I think, to classify color. But we still use the less favorable ways, like these different color standards, okay? I do not like this, but it is a standard. It's the National Institute of Justice Standards 604.01, and it has the reagent for the colors, like here, the Ducanol-Levene for THC. And if you do that and you do the ethanol extract and add that reagent, these are the colors that you get from the cannabinoids. I really wish they were RGB values. If they were RGB values, I could go into PowerPoint, Excel, Word, doesn't matter, anything on a computer, and I could type in the RGB values and I could see what that color was. Here you've got to go to the Munsell system, and it's 7.5 PB 4x4, okay? And so the 7.5 PB is here. We've got PB, purple, blue. Here's purple, blue. So here's PB right here. That's a 5 PB. This is a 10 PB. So 7.5 would be right between those two. So we know it's going to be somewhat between these two colors. And that, I mean, it works, right? But I like RGB way better. But this is the standard. And then compare that to T, right? So 5 green, yellow. So we go over here, here's green, here's yellow, here's the 5 green, yellow. So it'd be right there, and it'd be an 8-6. So those are the value and the hue. So here's a 6, and here's an 8. So it'd be pretty dark, okay? If it was an 8-10, it would be very faint in light color, like a pastel blue, green, blue. If it was, an 8-2, it would be really, really dark, almost black. So, and so you can see how we can classify the different colors. We could tell the difference between aspirin and codeine, because aspirin would come in at a 5 red, which is right here, and codeine would be a 7.5 purple. So here's a 10 purple, here's a 5 purple, so 7.5 would be right in the middle. And so it'd be somewhat between those two color swatches. Yeah. It works, I'm not going to say it doesn't work, but it's you can convert it from the Munsell system over to CIE XYZs, and then from there you can get to RGBs. I've never written that Excel tool, but one of these days maybe. Now here's the I went ahead and found the NIJ standard. It was referenced in the text, and so then I went out and found it and put it on the blackboard. So you guys, if you're curious, you can look at all the different substances you can test with color tests and see all their different colors. So here's all of these. This is just the first part of the table. We got methadone and procaine. We talked about that in this course. Quinine, mace, nutmeg, tea. You know, you don't want to just have drugs. You want to have things like tea. I wish catnip was in there. I got a cat when I was in college. It was a sophomore, junior, and a buddy of mine had a cat too. So we were running through the pet store, and there was like a brick of catnip. I did not need that much catnip, and I was like, "Hey, you want to go halves?" And he goes, "Yeah." So we bought this catnip at halves of like $3. Still, college students. So we get that, and so he takes the package, and I stuffed the rest of it in a Ziploc bag. Okay, and I put it in my car, and I forgot about it. Okay, now this story could be way better than it is. One day I was like, "What's under my seat?" And I pulled out. I was like, "Oh my gosh! I've been driving around with this green plant-like material under my seat, in the front seat of my car for weeks," and I never got into trouble. But you could imagine a police officer saying, "What's this?" "It's catnip." "Right." Right? But a color test would have said, "Yeah, it's not pot. I don't know why this guy smoking catnip." No, it's like, "Look, I have a cat. I got the receipt." You know, I don't know if I had the receipt, but anyway, you could definitely tell. So maybe catnip's in here. I don't know. But you know, extract the tea, light and yellow green. It's a green 5GY86, and you could do this. You know, phenobarbital, light purple, the 5P78. So you have all of the different color tests and the reagents in here. Zooming in, we got some more, the LSD and mace. Yeah, so it's pretty sweet. And then this is showing you the very small amount of change that you get with a huge color. You guys are very familiar with phenolphthalein, right? We did phenolphthalein for our acid-base detector. And all we did for phenolphthalein is rotate this acid group right here. So in Gaussian, I was able to figure out what changes happen when you titrate the phenolphthalein indicator, and this acid group rotates, and you go from a colorless substance to a strongly colored substance. And so it's pretty sweet. So that's it. We got a little bit early. You got some time to study. Now let me talk about the data audit I did this morning. So I went through. I put comments in there. Everybody was doing pretty well. There's a few folks that lost some points for missing more than a week's worth of data. So, and I put comments on, but I didn't take off points if you just hadn't done it for just this week. Like if you haven't taken data from Monday, here it is, Thursday. But it's supposed to be a daily task. So that's part of the exercise is like, okay, I got to do this every day. And that is a pain, but life is a pain, especially if you're in a lab that has to document, you know, your stuff. You've got to do it every day. You can't wait till the end of the week, even though it's due at the end of the week. Try to get to where you're doing it every day, and you certainly shouldn't go more than a week. So I put in there, if it was just this week missing data, I put, please count your data every day. If it was more than a week, I took off like 5 points. Again, that's not huge, but it's enough of a like sand in your shoe that you got to do something about it, right? And so that's it. Just go look at your charts. There was, oh, I don't remember who it was. They had a whole bunch of outliers. Was that yours? Yeah. I put a note in there. So go ahead and that's fine. No, that's fine. I looked at that and I was like, okay, so go ahead and recalculate the mean and standard deviation for your training period, but leave those outliers in because it's clearly shrunk your standard deviation too low because now a whole bunch of things are out of control. Did you do that?